So now that we've got that out of the way, we can start looking at the individual parts of the molecular partition function. So we're going to break this down into parts, and then those get multiplied together to get our overall partition function. So first we're going to look at translational energy. Just as a reminder of what this is, say we have a diatomic molecule, which I'll draw that like this. There are different ways that this can have energy, and one of them is just by having kinetic energy from moving around. All right, so just traveling around in the air. That's what we call translational energy. It's translating through space without like spinning or vibrating or anything like that. And so what we need to know are what are the energy levels of this type of energy. Kind of a weird thing to think about. The way we approximate this in quantum mechanics is through a system that we call a particle in a box, where we have a particle, like a molecule or something, trapped inside of a specific space. And that is basically like the translational energy. And what are the energy levels that this can take? And so these are walls that have infinite potential energy, has a specific length. This is the one-dimensional version. What we need is actually the three-dimensional version, because our molecules exist in three-dimensional space. And the energy levels associated with this, right, we need to know what are the EI values, so we can plug those into our sum to find our partition function. And we can solve this. There are 3 quantum numbers associated with this, one for each dimension, one for x, one for y, one for z. And this is a solution that you can obtain. We won't go through how this is obtained, but if you take or have taken quantum mechanics, we will go through this. And so this is the energy level expression. We have a bunch of different energy levels with, and to be specific here, the different n values can range from 1 up to an infinite number. And so we have a bunch of energy levels where, say, n equals 1 for all of them, then n equals 1 for one and 2 for the other ones, and we have a bunch of different possible energy states. But there are specific energy states. And so if we want to find our translational partition function, Q translational, well, we add up, over all the I energy levels. So we need degeneracy. In this case, there is no degeneracy. All of these are, there aren't any specific degeneracies. So we need to add up over all the different quantum numbers that are possible. So we can have nx from 1 to infinity. We need to add up from ny equals 1 to infinity, add up from nz equals 1 up to infinity, e to the minus beta times this energy expression up here. H squared over 8ml squared times nx squared plus ny squared plus nz squared. One thing I'll say is it doesn't actually affect much of anything, but this assumes that all of the lengths of our box are equal. If those lengths are different, the energy level expression looks a little bit different, but it doesn't materially affect the final results we'll get. Okay, well, this seems like a big pain. We have an expression, but what do we do with it? Well, one thing we can recognize is that we can separate this out into 3 separate sums and multiply them together because of the properties of exponentials, right? E to the a plus b plus c is equal to e to the a times e to the b times e to the c. So we can actually, since this is all just one giant exponential here, we can actually separate each of these terms from x, y, and z into their own sum. All right, so we're going to have sum from nx equals 1 to infinity, e to the minus beta times h squared over 8ml squared and x squared. Then we'll have a separate sum for ny that will look basically the same, except for we'll have y instead of x, e to the minus beta h squared over 8ml squared and y squared. And then a third term for our z dimension, e to the minus beta h squared over 8ml squared and z also squared. Okay, we've made a little bit of progress. This still looks like a big mess. Don't want to zoom in too far. Zoom out, zoom back in. So we what are we going to do here? Well, one thing to notice is that there's nothing fundamentally different about these three sums that we have. These are all identical because the range of x, y, and z is all the same, and they all have the same constants multiplying them. So we can simplify this a little bit and say, okay, well, Q trans, we'll just pick x as our example here. Q trans is equal to this sum for the x term. And we have 3 copies of it, so we can just cube this. Okay, so that's a little bit simpler. Now we don't have 3 different variables to worry about. But then the next question is, how do we actually evaluate the sum inside of this cube term? So I'm going to pause the video here, and in the next video we'll look at what do we do about this? How can we actually evaluate this?